Welcome to the part 2 of the water potential and osmosis notes. So, water potential is a way of looking at potential energy of water, and I would suggest thinking of it as free energy, like as we had with chemical reactions and enzymes, versus entropy, which would be disorder. And here's an example. So we've got two different solutions here. One, pure water. It's highly ordered. There's nothing mixed in with it. And we would say that has high water potential. And water over here has a lot of solute mixed in with it. It's got a greater degree of disorder, and therefore we say it has low water potential. So high potential, low potential. And while we're on the topic, we should probably make a note that this has higher concentration on the right, a higher concentration of stuff, more particles in it. So if we put this in numbers, we could say one solution might be 0.2 molar. That would have a lower concentration of particles than something that's 0.5 molar. And just as a review of what molar means, that means how many moles of solute there are per liter of solution. Solute, we're talking particles, things like salt or sugar. Solution, we're going to be talking about water in biology. Now, the potential, the water potential can be affected by a few other things. So just like you learned temperature was a measure of average kinetic energy of particles within a substance. Well, if we increase the temperature, we increase the energy of those things, we increase the disorder of those, that decreases the water potential. Remember, lots of disorder, lower water potential, kind of backwards. It also is affected by things like ionization. So we have sugar and salt to look at. Sugar does not ionize. It's not particles that are charged together getting stuck. It's a covalently bonded molecule. And when it dissolves, it stays as one piece. So either a ring of glucose or a double ring sugar or polysaccharides, things like that. Salt, on the other hand, if we take a mole of salt and dissolve it into water, it's going to ionize into sodium and chlorine ions, which basically doubles the quantity of the disorder. So we have to factor that in if we've got something that ionizes into two separate parts. I like to remind myself of gravitational potential energy. So if we've got, this is supposed to replicate like a dam and some water here. All right, so we've got the capability of making hydroelectric power by letting water fall downhill through this system because it has gravitational potential energy up here. It's going from an area of high potential to low. Okay? And the same thing happens with solutions and with water as it moves from high potential to areas of low potential. So you're going to need a couple of equations. There are a couple to manipulate here. The two basic ideas are these. So this is the solute potential. To calculate solute potential, it's negative I times C times R times T. That's as easy as it can be explained. I'll get more complex on the next page. The R and the T may look familiar from ideal gas law from chemistry. Yes, the R and the T are the same there. The other equation you'll need is this guy. It is total water potential relates to solute potential plus pressure potential. We said on the last video that the reason the potato did not explode is because it was able to equal the water potential of the outside water by having some solute potential, which is increased as we had some water dissolve into it, and we have pressure potential provided by the cell wall keeping it in. I do want to make a note here that we're talking about a difference in pressure between two sides of a membrane, not absolute pressure. Like you and I are underneath the atmospheric pressure. but we don't really feel it because the pressure on the inside of our bodies is the same on the outside. So, for instance, a cup of water just sitting there on your table, even though it's got 1 atmosphere of pressure on it, we would say it's got 0 pressure potential because there's not a difference from between two sides of the cup. Let's get into a little bit more on these equations. Water potential equations. Deja vu. We're going to use the, that's a psi, so like Raphael. So solute potential is negative. Negative here because we talk about the more stuff in something, the less water potential it has. The only way to make that happen is to have it be negative. So negative I times C times R times T. The I stands for ionization. A lot of the time, you're just going to use a 1 right here. So if you've got something that doesn't dissociate or doesn't ionize into 2 parts, like sugar, which we'll use in a few of our problems, then you just pop a 1 in there. 1 in an equation doesn't change anything. However, if we were to use, for the ionization, if we were to be dissolving salt, sodium chloride, those are 2 particles, so we would use a 2 in for that value of I. If we use calcium chloride, that would be 1 calcium ion, 2 chlorine ions, so we'd use a 3 value for that. So you can see how that works. It's not too complicated. Concentration, easy to work with. The units are going to be the molarity of the solution. R, ideal gas constant. This value may look familiar. You might have had the decimal point in a different place depending on what units you had before. So the one that matches up to this is liters times bars over moles times Kelvin. You may have seen it differently in chemistry, but you can work out ways to get these to equal one another. Bars are a unit of pressure. What is a bar? Well, it's 100 kilopascals. A kilopascal is 1,000 newtons per square meter. And atmospheric pressure for us is like 101.2 kilopascals, so a bar is almost an atmosphere. So I'm going to go ahead and use these units because I've seen them in a few examples. And if you think, oh yeah, a bar is about an atmosphere, we can have a general idea of what's going on the inside of our cells there. And then temperature, you got to have it in kelvins, not Celsius or Fahrenheit, so know your conversions there. We're cooking along. At equilibrium, your water potential within the cytosol must equal the water potential of the solution. These don't have to be the same concentrations because water potential is dependent upon 2 things. It's dependent on both the solute potential and the pressure potential. So if you've got pressure playing a role, it can allow you to be at equilibrium without being at the exact same concentration. And I want to come out and say it, our potatoes reached equilibrium. We give them 24 hours after all in the one that we did this year. So here's something that, I'm anticipating our graphs are going to look kind of like this. They're probably not quite as beautiful as far as my fake data there, but we've got change in mass on the y-axis, the concentration of the solution that they were put in on the x-axis, and if you did choose to do a line of best fit, we should have some sort of x-intercept here. I have a question there for you. What's the significance of the x-intercept? What does that tell us about our taters? And just as a refresher, hypertonic, the ones that were in the high molarity solutions reached equilibrium by means of losing water until the inside concentration was equal to the outside. So those ones did have the same concentration on both sides, and you can tell that because in those limp, flaccid potatoes, there was no pressure potential because the cells were all soggy. Isotonic ones, we had a couple that were kind of close, and they were already at equilibrium, so there wasn't a whole lot of change there. And then the hypotonic ones, those cells gained water until their solute potential plus the pressure potential, which increased as the cells swole, because they swelled against the cell walls, was equal to the water potential outside. So we have the solute potential inside the cell plus the pressure potential is equal to the outside water potential. Oh, shoot. Now we're all the way on to practice problems. I hope I'm ready for these. I have not done these yet, so if I stumble, I probably better do these as a separate video. Come back for the next one.